Integration by substitution. So here we're getting into, we've done all of the basic integration, and we even did integration with ax plus b, which had a basic chain rule. But sometimes there's more complicated chain rule questions, and then we will actually use a process called integration by substitution to solve those. And it really is quite beautiful. Okay? How do we know when to use this? The key is you see in the integral both an equation and its derivative are present. Or its equation and most of its derivative are present. So you really have to know your derivative rules well because it's in a process of recognition. Okay? So this was one that we did earlier in our derivative notes. Right after we did the chain rule, I had this question. Can you work backwards? And because you had just done the chain rule of bringing the outside function in front, keep the inside the same, multiply by the derivative of the inside function, working backwards, it was not hard for you to see that it would be this. And now, in integration, we would probably say, oh, we should add the plus c. No. I'll know if you write plus c, I assume that you know it could be any c. It's like any c, but I'm not including 7.3. Right? That would be not nice to all the 7.3 lovers out there. So, okay. So what we're going to find is we can do integration like this. Now this one worked out perfectly in that the 5 could come back up and not have to worry about dividing, and the derivative was perfect on the outside, no extra things, so it was easy. They're all like that, right? Yeah, right. They're not all like that. Okay? So here's some color coding. And in the color coding, what we notice, yes, I can borrow you. Anybody want a highlighter borrowing? Yes, and you have to use the right colors, that shade of yellow and that shade of, I'm just kidding. You want a yellow? Do you want two highlighters? You're good? You're going to highlight them in black pen beautifully. No, you're not going to have to highlight things on the test. The purpose of the highlightation shown here is just to see, oh, here's an equation and that's its derivative. Oh, there's tan. The derivative of tan is secant squared. And if the derivative and the original function show up, it's usually an indication that we can undo a chain rule to find these integrals. It is also usually the case that what's highlighted in yellow is also inside of another function. So can you see in the first one that the x squared minus 7 is inside the power of 4? And when you have the chain rule, the inside function stays the same, and then you multiply by its derivative. And we also have a choice in this first one. Can you see that if I had highlighted only the x squared, that its derivative would also be the 2x? But if something is inside, we're going to try to highlight all of it. And we're going to see why in a second. Everybody done highlighting? Everybody okay with the highlighting? Any arguments about any of the highlights? Oh, is anybody colorblind in this class? Good to go. Did anybody want to argue this one? Because isn't the derivative of cos also sine? Could I have highlighted it differently? Right, but then it would be a negative sign, so it doesn't quite work out. So this seems better to go the sine in yellow and the cos in green. But technically, and we're going to find this out in some of these questions, even if a coefficient is missing, it's going to be okay to highlight that way. Now, the notation is kind of messy, okay? And the notation is kind of funny because in our substitution, we tend to use the letter u for substitution. So we change this function, that's f of g of x, g prime of x dx, to just fu, du. Which sounds a little bit not appropriate, but it happens. Okay? So what ends up happening is we change it from a complicated looking derivative to a simplistic derivative. I can't believe they happened to record during the FU part. The one moment, the one, right, the one time that my calculus videos move from PG to PG-13. Yeah, we'll see. Whew. That'll be good. Okay, so we're going to look at what happens here. And there's also some interesting, awkward notation. And it's allowed, and actually the explanation of it being allowed is quite complicated. I probably can't do it off the top of my head. But what we do in the notation here is we decide, take out my highlighter, same thing as before, I have my original function in yellow, and I replace that with u. I notice my derivative right here, and with my derivative, I also highlight the dx. And I replace that just with du. And here's the reasoning behind it. If we do a substitution and we say that u is equal to gx, color coding it in the same way, if we take the derivative with respect to x of this side, we would get du dx. And if we took the derivative with respect on that side and change it to the other notation, we get g prime of x. Okay? So if u is equal to g of x, then the derivative of u with respect to x has to be the same as the derivative on the other side. That makes sense. What doesn't make sense that we're allowed to do is just decide, hey, with Leibniz notation, This means the derivative. Let's just break it up and imagine these are both things now, which they aren't, and move the dx to the other side by multiplying both sides by dx. Right? That seems like a notation fallacy that you shouldn't be allowed to do that. And if you're feeling that, that's probably okay to feel that. But it's actually, it works. It says, okay, if I multiply both sides by dx, then all of this together can be replaced with du. And there's a little bit of hocus pocus there because you took the dx on the bottom of one part and just moved it to the other side. Okay? But at this point, and you'll actually probably appreciate this, we don't have to explain why that works. Okay? And we'll just accept it. And it's like kind of nice that you can use another concept that you know, like multiplying both sides by something and thinking of it as a number, but it's not, but it's okay. All right? So, here's our first equation. We notice the derivative of the inside function is there. That the derivative of x squared minus 7 is 2x. So what we do is we say, let's make u the x squared minus 7. And then du dx, the derivative, would be 2x. And if I move the dx to the other side, then du would equal 2x dx. And now when we substitute this information back into our original equation, things get really simplified. The integral of u to the 4 du. And that's an easy integral to do, right? Because it's just a power. Add 1 to the exponent, divide by the new exponent, and plus c. We just have u to the 5 over 5 plus c. And now that we've figured our integral with respect to u, we can substitute back and be like, here's our final equation. It's going to be x squared minus 7 to the 5, all divided by 5, plus c. Yes, if you're going to use the substitution, okay? And some of you might say, I think I could do that one in my head, right? That's an easy enough one to do in my head. Perfect. I'll tell you, though, that the technique is going to be really nice, that even though you can do it in your head, you're going to like the technique, because there's going to be ones that your head's going to just say, sorry, Alan, I don't want to do this today. And then you try again in your head, and you're like, your head says, no, don't want to do this. So we'll see what those ones will look like. But for now, okay, great. And actually, I love it if you do it in your head. So let's look at the next one. Can you do it in your head? I know, that's the u part. But without doing the u, can you just do that integral in your head? Or does your head say, no, not this time? Yeah, right? Plus c. Okay? But again, we notice that in the inside function, the ln x, which is inside a power of 4, it's inside something else, its derivative is present because the derivative of the natural log of x is 1 over x, which could be written as x to the minus 1. So we can say, let u equal the natural log of x. The derivative is 1 over x. We can multiply both sides by the dx, a little bit of hand motion, pretending nothing happened. And now we substitute things back in, and it's that same easy one to do. So what do? Add 1 to the exponent and divide, and then we substitute back. And life is good. What is on your socks? Baby Semt?
He's a guy that dresses up in a devil costume and jumps around in front of the cameras in the Tour de France.
Okay. That's right. That would explain why I do not have socks like that. All right. Looking at it, can you do it easily in your head? There's some heads that are shaking now. It's like, ooh, I don't like this as much. It's doable. No, the fractions make your head even like struggle a little bit more, because this is really to the power of 1/3. Okay? So that would be something we are doing often, changing cube roots to fractional exponents. This is the derivative of the inside. Things work out nicely there, so we can say let u equal that. Then our derivative matches up. And when we substitute, it turns into something nice and simple. So add 1 to the exponent, divide by your new exponent. And this is where your brain was probably not very happy with the fractions. Multiply by the reciprocal so that you'd have 3/4 and substitute back. And once again, every time you do an integral, you can do the derivative right after just to check if you were right. And since doing the derivative is easier than doing the integral, that should be a fast way to check, right? This would be a chain rule. The 4/3 would come out in front, completely cancel everything out in front. Subtract 1 from the exponent, I'd get 1/3. That matches up. Then I need to multiply by the derivative of my inside function, and I would get 2x minus 3. That matches up. Okay, so at this moment, I'm having lots of fun. Are you liking these? They're like, this is your least favorite? Oh, I think it's so elegant. Is more fun? We get to do integration by parts. Some things that give you a hint that you should use substitution. There's a hint if you have one function inside of another function. That's a chain rule. Can you see that the sine x is inside of e? It's normally just e to the x, but now there's a sine x where the x normally is. Then, in addition to having a function inside of another function, that inside's function, its derivative is present. So the derivative of sine x is cos x. So that's the recognition you have to get good at. So what do we need? We need to be good at our derivative rules to be able to recognize these things. We have to be good at recognizing functions inside of other functions. So now I'm going to let u equal sine x, and its derivative is cos x, so we can replace cos x dx with du. And this changes our complicated looking integral, right? Can you do this one in your head? Sure, maybe, but you could probably do that a lot easier. Because it, yes? You could put the 5 out in front. Yeah. Or you could probably just imagine the 5 out in front. The integral of EU is EU. So you'd still have 5 EU plus C. And now we can substitute everything back. Yeah? Now that you see the answer, it's easy. But the problem with doing these in your head is there's a lot of data originally. What the substitution does is it breaks it down for you to easier data, so you can do one part, the easy derivative part first, and then just substitute back afterwards. Oh, they are just, it's just fun after fun after fun. Okay, try this one in your head. This is the hard one to do in your head. Harder than the other one so far. It's a fraction. And I think this is the one that's the hardest to see, right? Looking at it originally. Did anybody think of a natural log in this case? Does it, like, it doesn't scream natural log at all, does it? So what we notice is that the bottom, its derivative is on the top. So if we let u equal the bottom, then du dx is the top, which can get replaced with du. And when we put things in, can you see that you would have a u on the bottom of a fraction, which we'll write as 1 over u, or u to the minus 1. And that is the derivative of a natural log. Now, if I was doing the derivative of the natural log, right? If I was taking this and doing the derivative, I would say the derivative of natural log is 1 over, keep the inside the same, multiplied by the derivative of the inside, and I'd write it like this. Of course, this second thing is like over 1. It makes sense that you can multiply the tops, multiply the bottoms, and write it exactly as was written in our integral. And this sort of leads into what can sometimes make things more complicated is technically the way that it's written inside the integral is like simplifying this a bit. This wasn't really hard to simplify. But when you simplify things, you actually complicate things in many cases. Because things are harder to see. Oh, Aiden. Yesterday, when you weren't here. No, but we actually commented. we, we actually commented. I put up a question. I said, oh, I put up a question and nobody's complaining about the next question. And I don't know why you complain, Aiden, because I have the indication that you actually quite like math and science. But if you'd like, we can take a break and do a novel study. Oh, there's some English people that there's some head shakes going. No, no novel studies, no essays. Ooh. Okay. F, G. Try F and G on your own. I want to play around with H a little bit. It is a great sign. I'm going to just pause this because we're going to be working on our own for a bit. Here's a check on the first one. Did you make u 3e to the x? And then it just becomes cos u. Cos u. And then you get sine u plus c. Substitute back. No problems. No. What I do on tests is I usually, in this unit, give you one free I forgot plus c. If you forget plus c the second time, you lose 1 mark. If you decide to not write plus c on your whole test, you only lose a maximum of 1 mark on your test. So that if you forget it, I'm not taking, but just yeah, yeah. First time you lose a mark. Second time you forget it, lose 2 marks. Then lose 4 marks. Then lose 8 marks. I would have passed, but I forgot plus c on the last question. And I got 0. All right, second one. Did you see that u was 10x? And the derivative, and you're right, I did have a typo on this one. It's missing the dx. And so, we get negative cos u plus c. All right, I'm going to do h in 3 different ways. H number 1. The most common way is you make u equal to sine 2x. Now, the derivative of sine 2x has a chain rule. So it's going to be cos 2x times 2. But we don't have that extra times 2 in here. So when we rearrange this, we want to get the cos 2x dx by itself. So I'm going to need to move my 2 to the side with the du, and I have a half du is equal to cos 2x dx. And this is the first question we've had where our derivative doesn't match up perfectly. There's an extra times 2. But since that's a constant, I can rearrange things. And now when I substitute, I just have the integral of u, and then I have to write 1/2 du instead. Well, that 1/2 is not hard because we can add 1 to the exponent and divide. That half would just be a constant. It would stay out in front. And now we can substitute things in. And we get a final answer of sine 2x, all of that squared, divided by 4. If you wanted to write the squared in between the sine and the 2x, that would have been just fine. Method 2. I'll switch colors. I'll do it in blue. We're going to let u equal cos 2x. Because then du dx, the derivative of cos is negative sine, keep the inside the same, multiply by the derivative of the inside. Now we want to get on this side just sine 2x dx. So I'm going to have to divide by negative 2. So I get du is negative 1/2 in front of it. So now my integral will be u replaces the cos 2x, and then a negative 1/2 du replaces the sine 2x dx. In other words, I have the integral of negative 1/2 u du, which is an easy integral. Add 1 to your exponent, divide by your new exponent, plus c. Substitute back, and I get negative 1/4 cos squared of 2x plus c. And this is also the correct answer. But just because both of those are the correct answer, that does not imply that you just made an identity, which kind of is a little bit bothersome. Then when you think that if both answers are right, they're the same,
I like it when they are the same.
but they're the same in some aspects, but not in the same in all aspects. So they're not equal to each other. And then, method number 3. Okay, this is I like this one. So I have the integral. It doesn't even need substitution. What did we have? Sine 2x, cos 2x. Okay? No. I'm going to use the following identity. You know that 2 sine x cos x is equal to sine 2x from your identities unit in grade 12 pre-calculus. Right? I've got them all up on the board so you can cheat and look over there. Okay? So what is the problem here is I have sine times cos, but I don't have the 2 in front. In mathematics, when something's missing, you can just sort of kind of put it there. I'm going to put a 2 out in front. You're going to disagree with me at the moment, and that's good, because that's not allowed. But if I also put a half out in front of the 2, a half times 2 is 1, and you're allowed to put 1 out in front of anything and multiply it. Doesn't change what it's equal to. But now I'm going to add brackets here and say, now the formula matches up perfectly. So I could use the formula and substitute in, and this would give me sine 2 times 2x, 4x dx. And now I can do just a straightforward ax plus b integral, right? I can say the integral of sine is positive or negative cos? Negative cos. Try it again. Negative cos. We're going to try one more time. It's negative. So we'd have negative cos 4x. And because you would have had a chain rule where you have to multiply by 4, here we divide by 4 plus c. So it's equal to negative cos 4x all over 8 plus c, which looks completely different than our answer from before. But once again, if you would graph this and compare it to the graph of the other one, they don't quite match up. So they're not, yeah, that's still, you kind of feel like you just made an identity, but not quite. But fascinating, okay? So what this means is on your test or quiz, you just say, put down an answer and a note that said, oh, Mr. JR, I used a complicated technique that you do not understand or know, and this answer is correct. You'll just have to trust me. And then from that, I mean, from there, I would be, yes, Eric's calculus. From there, I would just have to give you full marks because that must be what's true. Yeah. Yes, that's right. You'd say, would you like me to explain it to you for 3 hours, or do you want to just give me the marks? Right? And you ask me Friday at the end of the school day on a very long school week. So, good strategies. So that last question, I mean, we did it in 3 different ways, but that last question was the first time where a derivative showed up, but not completely in the right form. Here's another example of that. Oh, yes. Right? Because we notice a function inside of another function, noticing that the 4x squared plus 1 is inside the e to the x. So that's telling us a chain rule should probably happen. But the derivative of the inside is 8x. And we don't have an 8x. We just have an x. And that's good enough. Oh, yeah, for sure. We can add 8s wherever we like. I mean, either you could have made an 8x by including a 1/8 and an 8 at the beginning of this question. But what we generally do more often is we say, okay, I'm going to make u equal to that inside function, that 4x squared plus 1. I'm going to find my derivative, and then I'm going to rearrange things so that I can get the x dx, which is in my original function, on one side of that equation, and then I'll have a 1/8 du on the other side. Okay? So when you go, if you're thinking about highlighting things here, right, we are going to replace, if the highlighter ever starts working, the 4x squared plus 1 with the u. Wait for it. It'll get there. It is. And I wanted to highlight in green. No, I wanted to highlight in yellow. So this is going to be, I know, we can at least waste another. I think the highlighter will work faster now. Sure enough. Oh! Disaster. Here we go. I love it when students get so much enjoyment out of my pain. Oh, thank you. It's reciprocal, right? So this is going to get replaced there. Then we rearrange things to get this x dx by itself, so this part will get taken out. Then what are we left with? Now we just have e to the u and 1/8 du. Which its integral is easy, and then we can substitute back. Plus c. And there we go. Happiness all around. Try the next one on your own. What's that? No, it isn't a good sign. It's looking very bleak, I think is the word I would use. Yeah. Yes, only 1 point, then you're fine. But if we go to Jack's new policy, right, where you double the amount of marks you lose each time you forget plus C. B, it would be interesting to, you could choose what type of mark deduction program you would like. You could choose the easier one, right? Or the harsher one, but the harsher one you get, like, start off with bonus 5 marks, right? So you have to be like, oh, but if you went for the bonus 5 marks, but you do too many mistakes, then it costs you more than if you would have just gone with the standard. Bonus 5 marks, all right. All right. Yeah. Then the bonus 5 wouldn't make that much of a difference. Oh yeah, our last question. So one of the things that happens, and hopefully when you get to your test, is you've done enough practice that when you see a question, you recognize, oh, this is this kind of question. So what kind of question is this one? We got a 1 over idea, yes, but just the form of the question when it says, given that f of 0 equals 4, find f of x. It's a solve for C question. So we're going to let u equal 4x squared plus 1. We can do our substitution. And we get a wonderful 1 over u, which is a natural log. So then, substituting back, we now know that doing the integral would get us f of x, and now we know that f of x is the natural log of 4x squared plus 1 plus c. And we're told that when x is 0, y is equal to 4, so you can plug in 0. And here you have to remember what the natural log of 1 is. Mental math. You will. What unit was mental math? I think it was a cumulative grades 1 to 12 process that apparently many students choose to omit. Oh, maybe we could start some sort of campaign for mental math. Like sort of like signs like mental math is good for mental health. And then there'd be people on the other side that would probably, mental math is bad for mental health. And then you could have like big shouting matches at the ledge.